Hello. So in this new series, we'll together study game theory. Okay, and the textbook we're going to use is the very famous one, written by Osborne and Rubinstein. Okay, so let's write that down first. It's called A Course in Game Theory. Okay, by Osborne and Rubinstein. Okay. 1994. Okay. And the version that I use is in 2011. Okay. So that's a pretty recent version. Okay. All right. So why game theory is very important? Right? So it's because that game theory basically studies how strategic agents or strategic decision makers interact, right? So the the basic or the most important idea behind game theory is that we must have some individuals or some organizations or something. So those agents they have to be rational, okay, and they must make their decisions strategically, and they need to have some interactions, right? So if two people they do not need to interact with each other, then game theory doesn't apply to this case, right? So that's something that we need to remember, or that's pretty a very important thing. Okay, so formally, game theory is a analytic analytical tool, okay, and which is to help us to understand some scenarios that we observe when the decision makers interact to each other, right? So, okay, decision makers interact. Okay, so in this very first episode, we'll simply cover the introduction or the some context of game theory, right? So we won't directly start the concept or the formal definitions of some games, but something this is actually more important than that, right? So more fundamental. Okay, so we often observe those situations or those phenomena when the decision makers they interact to each other, right? So that is when game theory comes into the play. Okay, so basically game theory is to study how decision makers they interact strategically, as we mentioned, and sometimes we can see a lot of interesting mathematical or probability models or some statistical models, right? Or something that is not strategic or that doesn't involve any decision makers. So we can often see those things, right? But normally, if we want to use game theory to model some situations or to model some problems that is related to those contexts that we see often, so we need to consider or we need to think about how do we actually provide or how do we actually construct this game with some some real or fake people or some agents that they behave rationally and they have some preferences and they have some payoffs. So and they have their strategies to earn some expected payoffs from the game, right? With some rational behaviors. So that's something that we need to consider if we try to from the perspective of creating some games or to providing some new approaches or to having some new games, right? So that's quite important to us to think about. Okay, all right. So so the as mentioned in the textbook in the 1.1 section, okay. So that is what we're going to cover today. So they mentioned that the basic assumption that that underlie this game theory are that the decision makers they are pursuing the well-defined exogenous objectives. Okay, so well-defined exogenous objective. Okay, so that's not something endogenous, right? So here they need to make sure that those decision makers they are going for some defined, clearly defined, some outside or some exogenous objectives. Okay, so that we can define those things for them before we actually let them to play the game, right? So in other words, this is something that we know as the rationality. Okay. Okay. Also, so the game theory takes into account that the knowledge or the expectations of other decision makers' behavior. Okay. So the knowledge or the expectation of the other decision makers' behavior. Okay. Other agents' behavior. Okay. So this means they inference or they reason strategically, right? Strategic. So we have a rational assumption and a strategic assumption, right? So those two things are very fundamental in game theory. Okay, good. So the game theory models they are pretty abstract, right? So they're some sort of abstract representations of the real world scenarios, right? So and we can see a lot of different applications of game theory, and sometimes we cannot distinguish from we cannot really distinguish the theoretical work or the applied work of game theory, right? Because sometimes if we want to innovate some fundamentals of game theory, or we want to have some new theories for game theory, then it's often that we have those intuitions for the theories from some real world applications of the games, right? So that's why we can always see a lot of very useful or the very important examples in the very theoretical work of the game theory papers. Right? Okay, but still, in this at this stage, we can still make tell the differences between the theories and the applications, right? So that's not difficult for us. Okay, good. So another thing is that the authors they also mentioned that game theory uses a lot of math, and especially in this textbook, right? So they is pretty elegant, and they use a lot of mathematical expressions and notations to express the ideas or to clearly mostly to clearly define the those concepts, right? Because using math, it's more easy and it's more like convenient and coherent for us to understand those concepts, right? If we define those things in a clear mathematical way. Okay. So the final the aim of the game theory is to understand the behavior of the how the decision makers interact strategically, right? Again, so that's the use of the math. But the more important thing is the actually it's the intuitions, right? math and intuition. Okay, so normally we can, as we just mentioned, we can see a lot of interesting mathematical models, right, from some textbook of mathematics or statistics or probabilities. But the intuition behind those math or probability models are actually the most important part in game theory, right? So people can have very different interpretations or explanations regarding exactly the same mathematical expression or some formula, right? Or some proposition or some theorem, right? Like what we have mentioned previously in the Bayesian persuasion problem or the information design problem. So actually, what they used is simply they interpret the Bayes theorem, right? So only and in a very elegant, a very useful way, and to help people to construct this approach to understand how that signal can induce the distribution over the posterior beliefs of the information receiver, right? So the only thing that they build on their theory is the Bayes rule, right? But the most important part is to how to incorporate or how to interpret the Bayes rule or the Bayes theorem to in a way that we can actually incorporate those sender and receiver, those strategic agents, and how to make this story happen, right? A useful and interesting economic story behind that. Okay. All right. So that's pretty much about the this part. Okay. And we have let's go to 1.2, this section. So in this section, they talk about the solutions, right? And mainly it's about the solution concepts, right? So so a solution formally is just a systematic description of the outcomes, okay? And later we'll have a clear definition for the outcome, okay? So a solution is a description of the outcome that may emerge in a family of games, okay? So solution is sort of an outcome, okay? So game theory simply suggests some reasonable solutions, right? So normally we need those solutions to be reasonable, okay? Of course, it will require some clear definitions of those things, okay? This is just a brief intuition for us to first understand what this is talking about, right? Okay, so later we'll see that this book, okay, this textbook basically covers some different parts or different kinds of games, right? As we you might know this, like strategic games or static games versus the extensive form games, okay? And that's one way to distinguish different games. Another way is to distinguish different games is to have perfect or imperfect information for the games, right? Okay. So those different kinds of games all relate to different solution concepts, right? So and they all have different sort of outcomes in equilibrium, and we'll talk about that later. Okay. So it could be static or strategic. That's what they call strategic, static game, or extensive game. Okay. Or we can differentiate the games by the information, right? The information set basically is, and we'll see the definition later. So it could be, the information could be perfect, and it could be imperfect. Okay. All right. And those, they could combine with each other, right? So we can have static perfect, static imperfect, and extensive perfect or extensive imperfect information game, right? So all those combinations have some very interesting models and games inside, right? Okay. All right. And another way to distinguish the different games is the cooperative and non-cooperative games, right? Cooperative and non-cooperative games. Okay. So all those games or all those solutions that we'll introduce in this range here, this is basically in the beginning or in the first part of this series or in this textbook, right? That's a non-cooperative first, and later if we have time, or if that's also interesting or useful, then we can also discuss about cooperative games, right? So that's a completely different setup or different environment of those games. Okay. So about perfect and imperfect information. So basically, okay. So in the models in the part 2 of this textbook are the participants. They're fully informed about each other's moves. Okay. And in the part 3, they may be imperfectly informed. Okay. So a very important note here is that we can talk about this later, but we'll have something to remember or to be careful is that, so this perfect or the imperfect information is talking about the information set. So so it means that so we'll clearly define that later, but so that would be something regarding the knowledge of the moves from one player to other players. Okay, so it will be regarding those actions and moves to distinguish, to have this difference between the perfect and imperfect information. Okay, but another completely different thing is that if we can recall the setup from the information design or the Bayesian persuasion game, right? So in that game, although there is a state, right? So that state or that state nature, although we have that random variable, okay, but actually it is a perfect information game, okay? So there is no information set in that game because those two players, the sender and receiver, they both have exactly the same belief on that state of nature, okay? And they know the other person's move, and there's no incomplete information about that, right? About the moves of other players. What they do not know is the state, right? So that will still be the perfect information game. Okay, so that's some useful note just at this stage. Okay. All right. So let's go back to the very first or the very beginning assumption of game theory is the rationality, right? So that's what is discussed in 1.4 section, rational behavior. Okay, so the game theory models, we often assume that each decision maker is rational, is completely rational. Okay, but but some researchers studied the different setup with bounded rationality, right? So that's something else, and that's also very popular and interesting to study. But here, in the traditional, in the standard game theory setup, it's assumption with rationality. Right? Okay. So the rationality means that the player is aware of his alternatives. Okay, so the player is aware of a lot of things. Okay, so that which includes the alternatives. Okay, so all those actions, all those strategies, right? So and this player also knows also has the expectations about any unknown variables. Okay. Okay. Any unknowns. All right. Also has a very clearly defined preference. Okay, so that's very important. With the preference, then we can have the utilities or the payoffs, right? Also, this player must choose the action deliberately after some optimization. Okay, so act from an optimization. Okay. So in the absence of uncertainty, then we have some elements which constitutes a model of the rational choice. Okay, so those are as follows. So the first is a set of actions. Okay, so a set of actions is A. Okay, and from this set, this decision maker can make a choice. Okay. Okay, and we said there's a consequence or there's a outcome, right? So here we'll leave the outcome to be defined later. So here we use this consequence. Okay, so a set of consequences, possible consequences, okay, is C. All right, and we will just use the names that is defined in the textbook, right? Okay, we just follow their definition. And a consequence function, okay, G is just a map from set A to set C. Okay, and that specifies this consequence with from each action. Okay, and a preference relation. Okay, it has to be a complete, transitive, and reflexive, and it's a binary relation. Okay, so it's complete, okay, transitive, and reflexive, reflex, binary relation. Okay, and we use this on the set C. Okay, let's see. All right. Okay, that looks pretty much like an algebra, right? And we should have that to be studied later, okay, if we have time for that. And that is should be studied from the very popular textbook of MWG, right? And they have a lot of sections discussing the preference relation. Right? Okay. So sometimes the decision maker's preferences, they're specified by giving a utility function, right? Now we have the preference, then we have the utilities. So a utility function, okay, u, is just a map from C to a real number, okay? And it defines a preference relation by the condition if we prefer x than y, if and only if ux is greater than or equal to uy, okay? All right. So given any set B, okay, which is a subset of A, any B of actions that are feasible, okay, in some cases, then a rational decision maker chooses action A star, okay, that is feasible. So feasible means that A is an element of B, right? So it's feasible and A star is feasible and optimal, right? So in the sense that, remember this consequence function, right? G, its input is just an action and the output is the consequence, right? Okay, so G A star, okay, and we prefer that to G of A for all the A in B, right? Okay, alternatively, this agent can solve the maximization problem or just max over this A, and the objective is the utility, okay, and we have this G of A here, right? Okay. So an assumption on which the usefulness of the model of the decision making, okay, depends is that the individual uses the same preference relation when choosing from different sets of sets B, right? So they're always using the same preference relation here. Okay. And that might be something to further consider if they do not have the same preference relation, and there might be some works related to that, right? Okay, of course. Okay, good. So in those game theory models, the individuals or the agents, they often have to make the decisions under some uncertainty, okay? So that becomes even more interesting, right? So, and we can, so let's talk about that. So uncertainty, all right? So those uncertainties could be some uncertainty about the objective parameters of the environment, okay? It would be about the objective parameters, like the state of nature, right? Or state of the world. And it could be they're imperfectly informed about the events or the plays that happen in the game, right? Imperfectly informed about events happen in game. Okay, and then we can immediately see that the differences between those two, right? With the examples that we just mentioned from Bayesian persuasion and versus the standard signaling game, right? So the Bayesian persuasion would be the case that there is some objective parameters like the state of nature, which is unknown to the players, right? But in the standard signaling game, like the job market signaling game, that those signal senders, they simply try to signal their private types, right? And those are sort of so and there's a very useful assumption for that kind of model to hold, is that it's often assumed those students or those employees, right? So they often have their private types, and what they have, this sort of private information is imperfectly informed for those information receivers, like the employers, right? And the way of modeling this, the personal private type versus the state of nature, are quite different, right? So that approach of the standard signaling game in the job market signaling game, that kind of approach is regarded as the perfectly informed about those events or those type distributions. So those could be regarded as the uncertain. The receivers are not, so they're uncertain about the moves of the nature, and the nature chooses the types for those senders. Okay, in that case, that's what we're talking about here. So those two cases are quite different, right? All right. So and what are the other sources of uncertainty? So it could be uncertain about the actions of the other players, right? Other players, and the example that we just mentioned, it could also be applied to this one, right? So it also works here. Okay, and of other players that are not deterministic. Okay, so it's random or stochastic, and it could be uncertain about the reasoning of the other players. Okay, about the reasoning or the inference of other players. Okay, so the reasoning or the inference, this relates to the beliefs, right? Okay, and we'll talk about those belief, the prior and posterior beliefs, and we used Bayes' rule to update those beliefs if the agents they behave in a Bayesian manner, right? So, and this is a very large, also a very large field of the game theory. Right? Okay, good. So, to model the decision making under uncertainty, so a lot of game theory models, they use the theories from von Neumann and Morgenstern, right? And from Savage, okay. from those people. So it means that the consequence function, okay, so the consequence function, so G, so that is stochastic and okay, stochastic and known to the decision maker. Okay. So for the for let's say for each element A in the action set, and the consequence GA is a lottery. It's just another name for the probability distribution. So GA is just a probability distribution. It's a distribution on C. Okay. So it's just a randomization over the C. All right. And then the decision maker is assumed to behave as if this agent is maximizing the expected value, okay, of a VNM utility function, and that attaches a number to each consequence. Okay. So then the agent is assumed, so this is simply an assumption, assumed, okay, to behave as if this agent is maximizing the expected value of a von Neumann-Morgenstern utility, okay, function that attaches a number, okay, to each consequence. Okay. So if the stochastic connection between the actions and the consequences, if that connection or that map is not given, okay, then the decision maker is assumed to behave as if this person has something in mind. So that's pretty subjective. Have that as a probability distribution in mind, okay, which determines the consequence of any action. Okay. So if connection between A and GA is not given, then it is as if there is a subjective distribution. Okay. Sort of in mind, okay, which is not explicit, which determines the consequence. Okay. Determine the consequence of the actions. Okay. All right. And when we see those examples, and we'll know what's the meaning of those definitions or those assumptions. Okay. So in this case, the decision maker is assumed to behave as if there's a sort of in mind a state space, okay, omega, and a probability measure. And we'll talk about the probability measure. What does it mean later? Over omega. Okay. And a function, G, which is a product of A and omega to the consequence. Okay, and a utility function U from C to a real number. Okay, so this agent is assumed to choose an action which maximizes the expected value of U, G, of A and omega. Okay. All right. So that's, and we see this a lot, right, in the papers that which deals the uncertainty. Okay. And that with respect to the probability measure. Okay. All right. Okay. So that's 1.4. Okay. So in 1.5, they basically mentioned something about the steady state and the deductive interpretations of game theory. So that's not quite relevant to the theories of game theory, but that's something that we might we could consider about in real life, right? And it could be some interesting research related to game theories, which talks about that. So there's some conflicting interpretations for the solutions of the strategic and extensive games. Okay, so some people they interpret the so it's called the steady state interpretation. Okay, so in that case, so what people think is that each participant knows the equilibrium and each simply tests the optimality of the behavior given this knowledge. Okay, so it's because that is already acquired from the personal long experience. Okay, so that's sort of one argument. The other direction, or the other main argument, is that is sort of called the deductive interpretation. Okay, so by contrast, it says that they treat the game in isolation, and it's called the one shot event. Okay, so we can see a lot of like sort of one shot, few shots, those algorithms in machine learning papers, right? So this is quite similar to that. So it's called one shot game, right? So that game is played once, okay, and they attempt to infer or to reason those restrictions that the rationality imposes, right, on the outcome. Okay, so and that they also assume that each player deduces how the other players will behave from the rationality assumption, right? So basically, this is some argument which is not very related to our series here, right? But something to know, right? Which is quite which is useful, but we won't talk about that for now. Okay. All right. So that's 1.5. Okay. So let's go straight to 1.6. So it's called bounded rationality. Okay. So as we mentioned, we are focusing on the completely rational assumption, right? But as we know that there of course people can study the bounded rationality, and it's simply for example, some players so we have a clear perception of the situation, or have a greater ability to analyze the game, right? But actually, like they gave an example like chess, right? So if we can completely rationally calculate or to solve this game, right? So there will be a sort of a strategy, as we know, the dominant strategy, like for the white chess player, right, who plays the white piece. So the if we can calculate everything to exhaust all the possibilities, and then we have the full rationality or the full computing ability to do that, then there'll be only one possible outcome. Okay, only one possible outcome with the rationality, right? But the most interesting part for chess or those or Go or those similar games, board games or the card games, is that normally we don't talk about card games, but only board games, right? With the full information. So the most interesting part is that we do not have a full ability for the or the completely complete rationality, right? We don't have that. So that makes not possible for a human being to implement a sort of a dominant strategy for a chess game or some sort of other games, right? So that's what they are talking about this abilities or this perceptions of those situations, right? And that's called the bounded rationality in reality, right? But here, since we're talking about the pure theoretical game theory models, and we also focus on the complete rational assumption here, right? So, but the bounded rationality would be very interesting to discuss if we have time later. Okay. All right. So now let's have some formal terminologies and some useful notations, and for us to use later. Okay. And which is defined in this 1.7 section. Okay. So the set of real numbers is R. We all know that. Okay, that's a pretty common notation. And the set of non-negative real number is R plus. Okay. And the set of vectors of n real numbers is Rn. Okay. And the set of vector of n non-negative real numbers is Rn plus. Okay. We have those notations. Good. Okay, for element x in Rn and y also in Rn, and we define x greater than or equal to y. This means that if xi is greater than or equal to yi for all the i's, right? From 1 up to n, okay? Okay, so normally there are n players in the game. Okay, so that's sort of the notation for this textbook. Okay. And of course, we say that x greater than y if xi greater than yi for all I from 1 to n. Okay. Right, and we say that a function f from R to R is increasing if fx is greater than fy when x is greater than y. Okay, and it's non-decreasing if we change the sign to include the equality, right? Okay, and a function is concave if f of alpha x plus 1 minus alpha x prime is greater than or equal to alpha fx plus 1 minus alpha fx prime. Okay, So that's the concavity. Okay. Well, know that. I don't need to waste time to explain that. Okay. And that's for all the x and x prime in reals, and for all the alpha in from 0 to 1, including the boundaries. Okay. And given a function, okay, f from a set x to r, so we denote argmax over x to be the set of the maximizers of f, right? Okay, and for y as a subset of x, so we denote f of y as simply as the set. So this should be f x is an element of y. Okay. All right. So far, so good. Okay. So we use this as we mentioned. So there are n players, right? So we use n as the set of the players. Okay. All right. And we refer to a collection of the values of some variables, and one for each player as a profile. Okay. I will see a lot of those profiles later. So like the strategy profile or something else. Okay. So it means that for example, a strategy profile is a collection of those strategies from each player, right? So put them together in a set. So that is called the strategy profile, including all those strategies from each player. Right? Okay. So we denote a profile by it's just a family of sets, right? So a family of sets, okay, xi, I in n, okay. If I is an element of n, if that's clear, then we can just write xi, right, and with bracket. Okay. All right. So for any profile x equals to xj, j is in n, and any I in n, and we denote or we define x minus I to be the list or the family of sets to be the xj, and j is n, but we exclude I. Okay. So that family of sets of the elements of the profile X for all the players except I, right? Okay. So that's pretty straightforward. And given a list, X minus I, or given a family of sets, okay, those two are the same thing. Given that, xi equals to xj, x minus I equals to xj, j from n, but without I, had an element and an element xi, okay, so we have x minus I and xi together, then we denote that by x minus I and xi, okay. So this is the profile of xi, I, right? So together this is just itself, right? So xi, the family of the set itself. Okay. If xi, this is a capital X, so if is a set, okay, for each I from n, then we denote x, so this should be a capital X as well, x minus I, to be the Cartesian product. Okay, so this is a product, Cartesian product, okay, from J over all the J's, right? And J is from n and excludes I. Okay. And this is xj. All right, so this is just a notation, right, to define some sets. Okay, and we'll recall that later when we meet those notations later in the examples or in some chapters later. Okay, so that's the set of players, and we also have the binary relation. Okay, use this notation. So a binary relation on a set A, so that should be so that is complete if A is preferred to B or B is preferred to A for every A in A and for every B in A. Okay, so that's complete. And how about reflexive? So it's called reflexive if A is weakly preferred to A for every A. Okay, and it's transitive. So those are quite similar to the properties of algebra, right? Or field, sigma algebra. So transitive if A is weakly preferred to C whenever A is preferred to B and B is preferred to C. Okay. So a preference relation here that we use in game theory is complete, reflexive, transitive, binary relation. Okay, good. And if A is preferred to B, but B is not preferred to A, then we can write A is strictly preferred to B, right? I mean, if A is weakly preferred to B, but not B weakly preferred to A, then we have A strictly preferred to B. Okay, so that's the notation. Okay, and if A is weakly preferred to B, B is weakly preferred to A, then we write this, okay? A and B are equivalent, okay? All right, so a preference relation is called continuous, okay? So a continuous relation, it means that if A is preferred to B, whenever there are sequences so those are sequences A, K, K. Okay, so this K is simply so this is just a notation for the sequence. Okay, so this is the kth element, okay, in this sequence. Okay, and this just omits some notation, and this should denote the range, right? Or it denotes it's the all those index, right? From which to which, okay, like from 1 to infinity or what, and it should be more complete than this. Okay, so this is just a notation for the sequence. So there are sequences AK and bk, okay, in A. So that converge to A and B, to A and B, okay, respectively, for which AK is weakly preferred than BK for all case. Okay. So that's a pretty standard definition for the continuous, for the continuity. Okay. And the last thing here is the quasi-concavity. Okay. So we say that a preference relation on Rn is quasi-concave okay, if for every B in Rn, the set A in Rn, and we have A is weakly preferred than B. Okay, if we have all those A's, so this set here is convex, then we call this preference relation is quasi-concave. Okay, and also it's called strictly quasi-concave if every such set is strictly convex. Okay, so that's correspondingly defined. Okay, so we can this is pretty abstract, and we can consider that to be a three-dimensional a picture or figure, right? To help us to understand that. So if we have a sort of a utility, which is the z dimension, the z axis, then if that is quasi-concave, then we have all those slices in each height of z, or in each those on each level of those utilities, then actually we can see that the utility function itself, it should be convex. Okay, and then that the utility overall the 3D plot is defined to be called as the quasi-concave. Okay, so that's how people define that concept. Okay, but we will only use that. We will only understand that more when we use that, right? Okay. So we let X to be a set. Okay, X is a set, and so this is just the cardinality of X. So it means the number of the elements in X. Okay, and a partition of X. So this is a pretty straightforward definition, and we don't need to bother to write that down. So a partition is just a collection of the disjoint subsets of X, and those disjoint subsets, they have a new union, and that union is X. Right? So that's how we define partition. That's pretty interesting definition, right? Okay, and we let N to be a finite set, and X is a subset of Rn, and we say X, so this is a capital X. So we see this small x is Pareto efficient if there's no y in X for which yi is greater than xi for all those I in N. Okay, so it means that this has to be very it has to be optimal, or it has to be efficient, right? So that's how we define this Pareto efficient here. So for and likewise, so it's called strongly Pareto efficient if there's no y in X for which the yi is greater than or equal to xi for all the i's, and some for some i's, we have yi is greater than xi. Okay, so that's even stronger. And we don't need to write that down, but we'll use that later if we see them. Okay, another important part here. Okay, the last definition actually that we'll discuss is the probability measure. Okay, probability measure. Okay, good. So a probability measure mu is what? Is just a function. Okay, so mu on a finite or countable set x is an additive function okay, that associates a non-negative number, negative real number, with every subset of x. Okay, so additive means that mu of b union c equals to mu b plus mu c. Okay, if b and c are disjoint. Okay, all right, and more importantly, mu of the x itself, the biggest one, can be 1 as the largest. Okay, so that's called the probability measure. Okay, so we can further clearly or more technically define the probability measure. Okay, so this is the definition given by Osborne and Rubinstein, but we can use some other definition more rigorously to help us to understand the probability measure. Okay, so let's change the color. Right. So so that mu, okay. So we have some requirements, right, for this function mu. Okay, so the requirements for this function mu to be a probability measure on a sigma algebra. Okay, so the requirements for the set function, okay, because function is working on a set, so set function mu to be a probability measure on a sigma algebra. Okay, we'll talk about that later, maybe in the next video. Okay, are that okay? So first, mu must give some results, or it must map from the set to a real number in a unit interval. Okay, must map to some number between 0 and 1, a real number, right? A positive real number between 0 and 1, inclusive. And it returns 0 for empty set and 1 for the entire space. Okay, so that's the first requirement. So the second is that mu must satisfies we just mentioned that also, right, in the other definition, must satisfy the countable additivity, okay, for all the countable collections E1, E2, and so on of the pairwise disjoint sets. Okay, so mu of union of all the EIs. Okay. This is the summation because we can add them up. Okay. Mu of EI. Okay. All right. So now we can see a very simple example. Okay, is that so if we say that we have some, let's just draw like a circle. It's not very round, but we say that this is a very round circle. So let's say we have 3 here, okay, and 1 and 2. So this is the whole space, the whole set here, omega 1, 2, and 3. Okay, so that probability measure on this set, okay, so it maps the sigma algebra for all those subsets. Okay, so that's very important. So we'll talk about that later. For all those 2 to the power of 3 events, right? So that's 8 events to the unit interval. Okay, so we have this real line. So let's say this is 0 and 1. Okay, so we have a half, 3/4, 1/4. Okay, so all right. So what we have here, we have the this should be the power set, right? Okay, power set of omega. Okay, so which simply has 8 possible 8 elements in that, right? Okay, we have this. All right, so it is nothing but empty set, okay, and 1 and 2 here, okay, and we have 3, and what else? We have 1, 2, okay, and we have 1, 2, 3, everything together. We have 1, 3, and we have 2, 3. Okay, we have all those all the subsets, right? So this is the power set of omega. So we need to specify. So this probability measure not only requires the those properties, but it also has to give to return all those results here, right? So it's basically we map this to 0 and those 2 quarter. Okay, this is a half, and 1 and 2 half, and 2 and 3, 1 and 3 3/4, 1, 2, 3 as well, right? Okay, and then we can see that why this is important, right? Due to the additivity. So that's because we map all those subsets to the real number between 0 and 1. Then we can actually add them up when we need, right? Although sometimes we do not need all of those subsets to be studied in some problem, but to be a valid or to be a valid probability measure, we have to specify all those subsets in the power set, right? Okay. So that's something, some definition for that. All right. So this is the should be the end of the first the very first introduction to the game theory, and later we'll discuss some to start our topics and the real games, right? In the next following episodes. Okay.